everyone, this is Kalpana here. In this video, we're going to solve a differential equation from higher order linear differential equation. So let's get going. Problem. Solve d square minus 1 into y equals to x sin x plus x square e power x. Let's find order and degree of the given differential equation. So here, highest derivative is d square, so our order will be 2. And highest power of the highest derivative is a degree is 1, right? Or just write the given differential equation as d square y minus 1 into y equals to x sin x plus x square e power x. We know that d is a differential operator. Then d square will be d square by dx square, right? So we can write d square y as d square y by dx square minus y equals to x sin x plus x square e power x. Here d square y by dx square is the highest derivative, so our order will be 2. And highest power of the highest derivative is a degree is 1, right? Now coming to the problem. Given differential equation, d square minus 1 into y equals to x sin x plus x square into e power x, which is an operator form. F of d into y equals to q, where f of d equals to d square minus 1 and q equals to x sin x plus x square into e power x. Okay. Now we need to find the general solution to the given equation, which is given by y equals to yc plus yp. Here where yc is a complementary function, yp is a particular integral. We'll find yc using the roots of the auxiliary equation of the homogeneous equation of the given non-homogeneous equation. Simply by putting RHS to 0, we'll get the homogeneous equation of the given non-homogeneous equation, and we'll find yp using 1 by f of d into q. So let's now find yc and yp. The auxiliary equation of f of d into y equals to 0 is f of m equals to 0, where f of m equals to, we have f of d square minus 1, right? Let's replace differential operator by m, so that we'll get f of m equals to m square minus 1. Then our auxiliary equation becomes m square minus 1 equals to 0. And you can write 1 as 1 square, and this of a square minus b square form. So we can write it as m plus 1 into m minus 1. Now equate each factor to 0. From m plus 1 equals to 0, we'll get m equals to minus 1, and from m minus 1 equals to 0, we'll get m equals to 1. So here the roots are minus 1 and 1. So m equals to minus 1, 1 are the roots of our auxiliary equation, which are real and distinct. Therefore, m equals to minus 1, 1 are the roots of our auxiliary equation, which are real and distinct, or we can call them as real and different. We know that when two roots say m1 and m2 are real and distinct, then yc will be c1 into one constant into e power 1 root into x plus another constant into another root into x. Now coming to our complementary function. Our complementary function looks like yc equals to c1 into e power 1 root into x plus c2 into e power 1 root, another root into x, right? Then yc will be c1 e power minus x plus c2 e power x. So we got yc now. Let's find yp. find particular integral using 1 by f of d into q. We have f of d and q, where f of d is d square minus 1 and q is x sine x plus x square e power x. This is equals to 1 by d square minus 1 into x sine x plus 1 by d square minus 1 into x square e power x. Okay. This is of 1 by f of d into x into v form, and this is of 1 by f of d into e power x into v form. Okay. We'll find each term separately for our convenience. 1 by d square minus 1 into x sine x. I'm taking the first term. And we know that this is of 1 by f of d into x into v form. Sorry. Yeah, x into v form. So now we are going to use the formula 1 by f of d into x into v equals to x into 1 by f of d into v minus f dash of d by f of d whole square into v. If f of d is d square minus 1, then f dash of d will be 2d minus 0, which is equals to 2d. Right? Now, let's apply the formula. X into 1 by f of d into v minus f dash of d, 2d by f of d whole square into v. So this is of 1 by f of d into sine ax form, right? For a equals to 1, we'll find d square, which is given by minus of a square, which is equals to minus of 1 square, which is equals to minus 1. Now let's replace d square by minus 1 in both the terms. Okay, here also we are having sine x, right? Then obviously we'll get for a equals to minus 1, for equals to 1, we'll get d square equals to minus 1. So in both the terms, we'll replace d square. We'll replace d square by minus 1 in both the terms. So we'll get x into 1 by minus 1 into sine x minus 2d by minus 1 whole square into sine x. See, the denominator is non-zero, right? This becomes x into 1 by minus 2 into sine x minus 2d by minus 2 whole square into sine x. This is equals to minus x by 2 sine x minus 2d by minus 2 whole square is 4 sine x. 2 ones are, 2 twos are. This becomes minus x by 2 sine x minus 1 by 2 into d of sine x. Here d is a differential operator, so we can replace d by dx for our convenience, or you can just write, or you can just find derivative of sine x in the next step. This becomes minus x by 2 sine x minus 1 by 2 into derivative of sine x with respect to x is cos x, or we can write this as minus of 1 by 2 into x sine x minus 1 by 2 cos x, or just take minus 1 by 2 common, then we'll get minus 1 by 2 into x sine x plus cos x. Therefore, 1 by d square minus 1 into x sine x equals to minus of 1 by 2 into x sine x plus cos x. Now coming to the second term, 1 by d square minus 1 into x square e power x. As I said earlier, this is of 1 by f of d into e power ax into v form, right? Now compare x square e power x with e power ax into v. Then for a equals to 1, we'll find d plus a, which is equals to d plus 1. Okay. So we'll shift e power ax towards left by replacing d with d plus a. And later we'll operate v with 1 by 4 of d plus a. Right? Now shift e power x towards left by replacing d with d plus 1. We'll get d plus 1 whole square minus 1 into x square, which is equals to e power x into 1 by expand d plus 1 whole square using a plus b whole square formula. We'll get d square plus 1 plus 2d minus 1 into x square. Here plus 1 minus 1 gets cancelled and is equals to e power x into 1 by d square plus 2d by x square. Again, this of 1 by some function of d into x for k form. Right? So for k equals to 2, we'll have derivatives till d square. Because we are having power 2, so we'll get only 2 derivatives of x square. Okay? And from here, we'll get all higher derivatives of x square 0. And now, 2d is a lowest degree term, so let's take 2d common from these two terms. This becomes e power x into 1 by, we don't have any 2d here, so let's multiply and divide 2d to the first term, plus 2d into x square. Now take 2d common from these two terms. We'll get e power x into 1 by 2d into d square by 2d plus 1 into x square. So you'll get 2d into d square by 2d is d square plus 2d into 1 is 2d, right? Now, here 1d gets cancelled and we can write this fraction as 1 by 2d into, we can write d by 2 plus 1 as 1 plus d by 2 into x square. Now, split this fraction as 1 by 2d into 1 by 1 plus d by 2 into x square. This is equals to e power x into, again we'll split this as 1 by 2 into 1 by d. And this fraction is of 1 by 1 plus x form, so we can write it as 1 plus x whole inverse later, right? Just write it as 1 plus d by 2 whole inverse into x square. This is equals to 1 by 2 into e power x into 1 by d into 1 plus d by 2 whole inverse into x square. Now we can expand this, or we'll expand this with using binomial series expansion formula. So before expanding 1 plus d by 2 whole inverse, let's find derivatives of x square. Derivative of x square is 2x and d square of x square is 2, or we can write d square of x square as derivative of d of x square. We know the value of derivative of x square, which is 2x. Again, we can write this as 2 into derivative of x, and derivative of x value is 1. So you'll get 2 into 1 is 2. Right? D cube of x square is 0. We can write this as derivative of d square of x square. We have the value of d square of x square, which is 2. Now find derivative of a constant, which is 0. Right? So from here we'll get all the higher derivatives of x square 0. In general, we can write it as d power k of x square equals to 0 for k equals to 3, 4 and so on. Okay. So by keeping these in mind, we'll expand 1 plus d by 2 whole inverse using binomial series expansion formula. We know that 1 plus x whole inverse equals to 1 minus x plus x square minus x cube plus so on, right? Now let's expand 1 plus d by 2 whole inverse. For x equals to d by 2, we'll get 1 minus d by 2 plus d by 2 whole square minus d by 2 whole cube plus so on. This is equals to 1 minus d by 2 plus d square by 2 square 4 minus d cube by 2 cube 8 plus so on. We know that all the higher derivatives of x square from d cube is 0, right? So we can neglect all the terms from here and we'll take only the first 3 terms. Okay. This becomes 1 by 2 into e power x into 1 by d into expansion of 1 plus d by 2 whole inverse is 1 minus d by 2 plus d squared by 4 minus d cube. Okay, let's write this term first. This step. D by 2 whole square minus d by 2 whole cube plus so on into x square. So here we can solve the second term in 2 ways. Okay, I'll show you later. So here we are going to neglect all the terms from here. Okay, just consider it as equation 1 for our convenience, because we are going to apply another method later. Okay, I'll show you another method also. So this is equals to 1 by 2 into e power x into 1 by d into 1 minus d by 2 plus d square by 2 square minus d cube by 2 cube plus so on into x square. Since d power k of x square equals to 0, for k equals to 3, 4 and so on, so neglect higher derivative terms or higher derivatives d cube, d power 4 and so on. Okay, so we are going to neglect all the terms from here. Then this becomes 1 by 2 e power x into 1 by d into 1 minus d by 2 plus d square by 4 into x square. Okay, consider as equation 2. Okay, see here we can just multiply all these 3 terms with x square and later we can apply the values, or we can multiply all these 3 terms with all these 3 and the remaining terms also with 1 by d, and you can apply these values later. Okay, so we'll see this later. This becomes 1 by 2 into e power x into 1 by d into 1 into x square, or just write these terms as 1 minus 1 by 2d plus 1 by 4d square into x square, which is equals to 1 by 2 e power x into 1 by d into 1 into x square is x square minus 1 by 2 into d of x square plus 1 by 4 into d square of x square is equals to 1 by 2 into e power x into 1 by d into x square minus 1 by 2 into derivative of x square is 2x plus 1 by 4 into d square of x square is 2. 2 gets cancelled, 2 ones are 2 2s. This is equals to 1 by 2 into e power x into 1 by d into x square minus x plus 1 by 2. We know that 1 by d is an integral operator, so we can apply integration here. Is equals to 1 by 2 into e power x into integral x square dx minus integral x dx plus integral 1 by 2 dx. So before operating integral, we'll just write the constant outside the integral. Is equals to 1 by 2 into e power x into integral x square dx minus integral x dx plus 1 by 2 integral dx. Now let's perform integration. We'll get x cube by 3 minus x square by 2 plus 1 by 2 into x. We can write 1 by 2 into x as x by 2. Now take the LCM of 3, 2. 6 is their LCM. So in the numerator we'll get 2x cube minus 3x square plus 3x. Right? In the denominator first term we are having 3, so close 3. Multiply this 2 to x cube minus the denominator of second term we are having 2, so close 2, and multiply this 3 to x square plus in the denominator of third term we are having 2, so close 2, and multiply 3 to this x. Got it? So this is equals to 1 by 2 into e power x into, now we can write this fraction as 2x cube minus 3x square plus 3x by 6. Now take x common from all these three terms. We'll get 1 by 2 into 1 by 6 into e power x into x times 2x square minus 3x plus 3. Okay, this becomes 1 by 2 6 are 12 into e power x into x is x e power x into 2x square minus 3x plus 3. This is the result obtained from the second term. Okay. I'll show you another method. So let's take equation 1 or equation 2. I'll go for equation 2, okay? It will be easy. So we have 1 by d into 1 minus d by 2 plus d square by 4, right? Minus, you'll get d cube by 6. I think 2 cube is 8 plus so on into x square, right? Is equals to 1 by 2 into e power x into, now multiply all the terms with 1 by d, then we'll get 1 by d into 1 is 1 by d minus 1 by d into d by 2 plus 1 by d into d square by 4 minus 1 by d into d cube by 8 plus so on into x square, right? 1d gets cancelled. Here you'll get d square, right? And from here you'll get higher derivatives d cube, d power 4 and so on. So we'll negate all the terms from here. Okay, or I'll show you the next term. The next term will be 1 by d into d power 4 by 2 power 4, right? So we'll get d cube by 2 power 4. See, we got higher derivative, right? So the terms from here will be omitted. We can remove all the terms from here. Then we'll get 1 by 2 into e power x into 1 by d minus 1 by 2 plus d by 4 minus d square by 8 into x square is equals to 1 by 2 into e power x into 1 by d minus 1 by 2 plus 1 by 4 into d minus 1 by 8 into d square into x square. This becomes 1 by 2 into e power x into 1 by d of x square minus 1 by 2 into x square plus 1 by 4 into d of x square minus 1 by 8 into d square of x square is equals to 1 by 2 into e power x into, here 1 by d is an integral operator, so perform integration for the first term, minus x 1 by 2 into x square is x square by 2 plus 1 by 4 into derivative of x square is 2x minus 1 by 8 into d square of x square is 2. 2 ones are 2 twos are 2 ones are 2 fours are. This becomes 1 by 2 e power x into integral x square dx is x cube by 3 minus x square by 2 plus x by 2 minus 1 by 4, right? So we can split the total terms in bracket as 2 terms, okay? I'll write it as 1 by 2 into e power x into x cube by 3 minus x square by 2 plus x by 2 minus 1 by 2 into e power x into 1 by 4. This becomes 1 by 2 into e power x into, take x common from all these three terms, or better, firstly, okay, take x common, then we'll get x times x square by 3 minus x by 2 plus 1 by 2 minus 1 by 2 into 1 by 4 is 1 by 8 e power x. Now take the LCM of 3, 2, 2. LCM of 3 and 2 is 6, right? So we'll get 1 by 2 into x e power x into 2x square minus 3x plus 3 by 6 minus e power x by 8, or we can just write it as 1 by 8 into e power x. You'll get the same thing. You can write it as 1 by 6 into 2x square minus 3x plus 3 minus 1 by 8 into e power x, which is equals to 1 by 2 into 1 by 6 is 1 by 2 6 are 12 x e power x into 2x square minus 3x plus 3 minus of 1 by 8 into e power x. Okay, this is by using second method, and here by comparing these two answers we have 1 by 8 e power x extra term by using second method. Okay, later in the general solution we'll add this 1 by 8 e power x to this constant. Okay, then we'll get the same answer. Fine. Okay, now coming to yp. Yp equals to, result obtained from the first term is minus 1 by 2 into x sin x plus cos x, and result obtained from the second term is, I'll go for the first one now, 1 by 12 into x e power x into 2x square minus 3x plus 3, or yp equals to minus 1 by 2 into x sin x plus cos x plus result obtained from the second method of second term is 1 by 12 into x e power x into 2x square minus 3x plus 3 minus of 1 by 8 into e power x. Now we got yc and yp, right? Let's write the general solution. The general solution is given by y equals to yc plus yp. Then by using first yp we'll get y equals to yc, c1 e power minus x plus c2 e power x minus 1 by 2 x sin x cos x plus 1 by 12 into x e power x into 2x square minus 3x plus 3. Okay, or by using second yp we'll get y equals to c1 e power minus x plus c2 e power x minus 1 by 2 x sin x, here you'll get plus cos x, okay, plus cos x plus 1 by 12 into x e power x into 2x square minus 3x plus 3 minus 1 by 8 into e power x. Or add this with constant, we'll get y equals to c1 e power minus x plus c2 minus 1 by 8 into e power x minus 1 by 2 into x sin x plus cos x plus 1 by 12 x e power x into 2x square minus 3x plus 3. Okay, this is again a constant. Okay, always remember that the answer varies with the method we choose. Fine. So we have seen a problem from higher order linear differential equations in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.